Stephanie Howard. I am a postdoctoral researcher at Goddard in their planetary magnetospheres lab, where I mainly do research related to data that comes in from Maven, in particular the magnetometer instrument. And like she said, Maven is getting ready to celebrate its 10-year anniversary at Mars. Well, its launch was actually just a Saturday, but then in a few months it will have been its 10-year anniversary at Mars, and it has been sending back amazing data that entire time. So today I'm just going to give a rather broad overview of why the Maven spacecraft came into existence, what we were hoping to answer, what questions we were wanting to answer with it, and how it has helped us over these past 10 years. So to start off with, just what was the motivation for Maven itself? Maven's primary science objective was to study the climate history of Mars and how that climate at Mars has changed and evolved over the nearly 4.5 billion years of the planet's history. Because today, Mars is a very arid, dry, cold planet. But when we look at the surface of Mars from other spacecraft or some of the rovers that are on the planet, we see this abundant evidence that at one point in Mars's history, there was probably water on the surface itself, and that it was in liquid form and it flowed across the surface. You can see some of these images here that help support that, where you see these outflow channels from what look like water flowing across the ground, things that look like what we would consider river deltas here on Earth, various kind of rock formations and minerals that we associate with liquid water. So there's a lot of evidence that at one point Mars had water and it was very abundant on the surface, but now there's nothing there. So what happened to it and why did it go away? Well, we think one of the reasons Mars doesn't have water anymore is that it's because its atmosphere has changed over time. Today, Mars's atmosphere is only about 1/10 of what Earth's atmosphere is in terms of density. So it's a very thin atmosphere. And that type of atmosphere is not necessarily good for keeping in water and heat. So it's likely that much earlier on in Mars's history, it had a much denser atmosphere that kept the planet much more warm and kept in that kind of liquid water that we would expect to create some of those formations. But then the question arises, if Mars did have this denser atmosphere, why does it no longer have it today? So what happened to this atmosphere? And it turns out that one of the things that could have happened is the atmosphere was just lost to space over time. It slowly eroded away. And the way that works has to do with how the sun interacts with things in the solar system and the solar wind in particular. The solar wind is it's a plasma that is constantly streaming off from the sun. So it's this high speed stream of electrons and protons that is constantly flowing out from the sun itself, and it's interacting with everything in the solar system. And in the case of Earth, we have a global magnetic field that holds off this solar wind and keeps it from impacting directly on the atmosphere. However, Mars doesn't have this, or at least it doesn't have this today if it ever had it at all. So whenever this solar wind is streaming past Mars, it can interact directly with the atmosphere of Mars itself. And there are several processes that could cause the streaming solar wind as it flows past to slowly strip away parts of the atmosphere. And so it's believed that over time, this streaming solar wind slowly eroded away the atmosphere, and we're left with the atmosphere that Mars has today. So Maven was, or as its full name is called, the Mars Atmosphere and Volatile Evolution spacecraft, was conceived of as a way to study the upper atmosphere of Mars and how this upper atmosphere interacts with the sun and the solar wind. That was its big kind of overarching science, is we want to know what happened to Mars's atmosphere over time. So enter the Maven spacecraft itself. You can see here in this picture on the left, this is the actual Maven spacecraft before it was loaded up in the nose cone of the spacecraft and launched into space. You can see the main features you're seeing here is, you know, the large solar arrays, which is mainly what powers the spacecraft, and also the high gain antenna, which is how it communicates with Earth. The spacecraft itself is about the length of a school bus, and it weighs roughly the size of an SUV. However, one of the basically important parts of the spacecraft are in fact the scientific instruments that it carries to help us carry out these science investigations. The instruments are roughly divided into various suites of instruments. The biggest suite being the particles and field instruments, which I will come back to in a minute. But it also has what's called a remote sensing suite, which is really just an imaging ultraviolet spectrometer. This is an instrument that looks at ultraviolet wavelengths. In some ways, it operates similar to a camera, but it takes a look at things in the ultraviolet. There is also the NGIMS, or the neutral gas and ion mass spectrometer, which is considered its own suite. And it is, in particular, looks at the composition of both neutrals and ion particles that Maven is flying through. This is particularly good at looking at things like the atmosphere itself and seeing, or other denser components and looking at that. But back to the bigger suite of instruments, which are the particles and field instruments. These instruments are mainly designed to measure charged particles and electric and magnetic fields around the spacecraft. So you have the SWIA and SWIA instruments, which are the solar wind electron analyzer and solar wind ion analyzer, respectively. They measure, as the name implies, the electrons and the ions, mostly in the solar wind, so the lower energy of the electrons and ions, and occasionally some of the planetary ones are just, you just get kind of the energy of these ions coming through from that instrument. You also have the static instrument, which is the superthermal and thermal ion composition instrument. This instrument, and it measures ions similar to SWIA, but from this instrument we can also get what type of ions we're looking at, what species of ions. Is it oxygen? Is it carbon dioxide? Is it hydrogen? Something like that. We also have the SEP instrument. This one, as the name implies, is the solar energetic particle instrument. These solar energetic particles are higher energy particles, typically ions. They're also typically coming from the sun itself, and they will impact Mars. This instrument measures those and picks those up. You have the magnetometer, which is a basic, just measures the magnetic field. It measures magnetic field in 3 different directions and sends us back what it's seeing at the location of the spacecraft. And then you also have the Langmuir probe and waves instrument, which is an instrument called a Langmuir probe. And it's good at telling us plasma features or plasma properties. You can get things such as electron density or the electric potential of things in the area. And these instruments are what we are using to try and answer this question of how is Mars interacting with the sun and the solar wind, and how has this changed the climate of Mars over the ages. So just a basic timeline, the spacecraft it launched from Cape Canaveral on an Atlas V rocket on November 18th, 2013. It spent about 10 months traveling to Mars itself and reached Mars on September 22nd, 2014. You can see here in the pictures on the upper right is the actual launch of the rocket carrying Maven, and then a cartoon that shows the trajectory of how Maven got to Mars itself. Once Maven was at Mars, it took another month or so to adjust its orbit down to the final science orbit, and it started up all of its science instrument and started taking data. So the final orbit, at least for the first part of Maven's lifetime, was a 4.5-hour science orbit. So it completed one orbit every 4.5 hours. It was a very elliptical orbit around the planet, where on closest approach or periapsis, it was typically around 150 kilometers from the surface, but it would reach out at apoapsis, or furthest away, it would get out approximately 6,000 kilometers above the surface of Mars. So a highly elliptical orbit. but this orbit precessed as the orbits progressed. So the orbit changed the location of where it was over the planet so we could map the properties of the entire planet itself. It changed both the latitude or the north-south component and the local solar time, which is equivalent to almost east-west, or basically how basically what time of day it is over the planet whenever the spacecraft goes over it. And this allowed us to map the properties over the entirety of the planet itself, given enough time. So what I'm going to do for the rest of this talk is very briefly and very broadly go over how what Maven has contributed to the science and our understanding of Mars in the past 10 years. And this is, like I said, Maven has 10 years worth of data sending back. We are still researching. There are a lot of people who have spent the past 10 years using this data to advance the science. So what I will be mentioning is a very broad overview of just some of the major highlights that have come out of Maven. But Maven has, the contributions Maven has made vastly extend whatever I could fit into this very short talk. But one of the biggest areas Maven has contributed to, which is as it was designed, is atmospheric escape at Mars. And so as we've seen with Maven and the nearly 10 years worth of data it has sent back, we have a better understanding now of how we believe the atmosphere was stripped away from the planet over the years. And as we see, we believe again that as the solar wind impacted the atmosphere, there are multiple processes that it could use to strip away parts of the atmosphere as it goes. One of these is that the water on the surface of Mars could have evaporated out as those individual water molecules rose higher into the atmosphere. They could become energized by the solar wind and broken down into their component oxygen and hydrogen. And then if those particles became energized enough, they would be carried away with the solar wind itself. So that is one possible process. There's other processes involved in that that could also strip away parts of the atmosphere, which we already had an idea of how some of these we thought worked before Maven got to Mars. But Maven made some interesting contributions to our understanding of it. In particular, it helped us understand that the escape rate of the atmosphere at Mars is not constant. We now think that the escape rate is higher whenever Mars is closer to the sun. So Mars's orbit around the sun is not an exact circle. It actually is a little bit more of an ellipse. And so at times, as it goes, like in a full Martian year, it will during parts of that year be closer to the sun than others. And as we have many years long, like many Martian years long observations from Maven at this point, we can see how that escape rate of the atmosphere changes as Mars becomes closer and further from the sun itself over the years. So that was one contribution to atmospheric escape Maven made. In addition, we have also seen that atmospheric escape and atmospheric loss can be especially notable during solar events. So solar events such as ICMEs or interplanetary coronal mass ejections, which is when you get a strong, basically a solar storm almost, you get a strong event coming off from the sun itself. And if that outburst from the sun impacts Mars, it can strip away a lot more of the atmosphere than would happen on a day-to-day basis just from the solar wind itself. And we know this because Maven was at Mars when some of these ICMEs came by and impacted the planet. And we've been able to observe what happens when those impacts occur and see how this affects this atmospheric loss. So those are some of the more notable contributions to atmospheric escape we can credit just to Maven itself. Now, in addition to atmospheric escape, we were lucky enough that Maven got to Mars just in time to observe the comet sighting spring and its near flyby of the planet. This here is an image taken from Curiosity on the surface of Mars of the comet sighting spring whenever it was passing by the planet. As you can tell, it passed by in October 2014, which, as I said, which is just a month after Maven's arrival, which is right around the time Maven basically came online as a science instrument and could start taking data. But we did get it up and going in time to catch some interesting data from this comet. And we instruments in particular, the IUVS instrument and INGIMS, which again looks at ion composition, got some very good measurements from this comet and how it interacted with the planet to help us understand better, get a better picture of what was going on. And this was entirely coincidence. We did not know this was going to happen when we were planning the mission, but it worked out very nicely in our favor. So this was a big highlight for Maven, especially early on. The last science highlight I'm going to briefly talk about is the aurora at Mars, which Maven has helped contribute a lot of understanding to. So the aurora, as we know them here at Earth, are generated when energetic charged particles interact with our global magnetic field and are channeled into our atmosphere from our global magnetic field typically. However, Mars, like I've mentioned previously, doesn't have this global magnetic field. So the mechanics of how aurora work at Mars are quite different, yet we still see aurora. They're not quite the same, but we see them. And there are multiple different types of aurora at Mars, actually. So you get, most recently we've discovered a discrete aurora, which are these individual auroras that we can pick out in the UV from the UV instrument. And it's believed that these are possibly caused by charged particles interacting with the crustal fields at Mars, because while Mars does not have a global magnetic field, some of the surface of Mars is highly magnetized and has strong crustal magnetic fields in specific regions. And so if charged particles interact with that, we believe this is what's causing that diffuse aurora that we're seeing, that we've picked up on recently. There's also a diffuse aurora, which is believed to be generated in some way by electrons interacting with the different magnetic fields around Mars itself. Not necessarily just not a global magnetic field, but either they're getting down interacting with the crustal fields or the magnetic fields coming off from the sun that are impacting Mars. But this aurora is seen kind of broadly in broad regions over the planet, and it's actually much closer to the surface than any type of aurora we would see at Earth, because the electrons at Mars can get closer down to the surface of the planet than anything we could see at Earth itself. In addition to those two aurora, we also have spotted proton aurora at Mars. And this is a phenomenon that has sometimes been seen at Earth before, so it's not new, but it is, it's basically caused by, instead of electrons, protons interacting with the cloud of hydrogen basically that surrounds Mars. Since hydrogen is a very light element, it diffuses further out from Mars itself than some of the other atmosphere, and protons interacting with this hydrogen, we believe, is what's causing this proton aurora, which is again a very diffuse, broad aurora that we can see at Mars. So, like I said, Maven contributed greatly, especially the IUVS instrument in particular, helped us pick out this aurora at Mars and see the multiple types of aurora at Mars. So these science highlights, like I said, these are just 3 of the many contributions Maven has made to Mars science over the past 10 years. And we hope Maven will keep going for many years to come. Currently, all the science instruments are still functional on Maven. It is still operating, everything is still operating as it should for the most part. However, in addition to doing science, Maven also is serving as a communication relay for other spacecraft and rovers at Mars itself. Back around 2019, Maven performed what was an aerobraking maneuver that adjusted its orbit. It lowered the periapsis to around 130 kilometers, and it also lowered the apoapsis to around 4,500 kilometers. So it overall lowered the orbit and made it slightly more circular so that it had better communication to these ground assets on Mars. And so now Maven, in addition to sending its own science back to Earth, is relaying science from things such as the rovers or InSight on the Mars surface. And this is actually means that Maven currently holds the record for the largest data volume returned to Earth because it's sending all this data back. And like I said, currently Maven is still functioning as intended, and we hope it will continue for many years to come and keep sending us back all of this great data that we can use to advance the science of what's going on at Mars. So I will end my talk there by saying thank